Section 14.3, change of variables, specifically into polar coordinates. So let's begin with a quick recall of the polar coordinates. Okay, so we've got x is equal to r cosine theta, y is equal to r sine theta. R squared is x squared plus y squared, which means r is the square root of x squared plus y squared. And we do, just out of convention, we're going to keep r positive. R can be negative, but for us, we're going to keep r greater than or equal to 0. And theta, we've got tangent theta is equal to y over x, right? And we've got theta between 2 pi and 0 and 2 pi. Can't write and talk at the same time. So theta is between 0 and 2 pi. Okay, so as you've seen in the past, there are definitely times when it's easier to describe something in polar coordinates. For us, that is going to be sectors. Okay, we're going to describe sectors that way. We're going to describe rings in polar coordinates, and we're going to describe cardioids in polar coordinates. Cardioids. All right, so let's take a look at these. So a sector of a circle, right? We've got some angle theta, and it has some radius r. This is going to be our region. Okay, so if theta goes, in this case, because I'm going from 0 degrees to pi over 2 degrees, we would describe our region as being the set of all r theta, such that r is between 0 and r. Let's call it r1, just so we have some value. So 0 is less than or equal to our radius is less than or equal to r1, some specific value that we're giving it. And theta, in this instance exactly, is from 0 to pi over 2. Now, of course, I could have drawn a different sector to where it didn't go a full pi over 2. Maybe it went pi over 3, or maybe it went something random like 1.8 radians, whatever the case may be. But this is how we would set this up. So here we have pi over 2 for theta, going from 0 to pi over 2, and then we've got our radius going from 0 to r1. All right, so now let's look at rings. So a ring is going to look like this. Right? So we have some interior R, so it's the region in here. It's the pool float. That's what it is. It's this region here that I have in green. So we've got our inner radius R1, our larger radius R2. Cannot see those. So this is R2. This right here is R1, right? And then let's say, just for the fun of it, well, now, I'm not going to give them specific numbers, but as you can see, theta is going all the way around, right? So theta is going all the way around, from 0 to 2 pi. So if we want to set this region up, we could set it up like this. This is going to be the set of all r theta, such that r is between r1 and r2, and theta is from 0 to 2 pi. And that gives us the entire ring. Finally, cardioids. Cardioids, I think they're called cardioids because they kind of look heart-shaped. So let me draw one for you. So here, we're going to take this one where r is equal to 3 plus 3 sine of theta. Okay, it's going to come out and it's going to look like this. Wow, that was atrocious. Let's try that one more time. It's going to come out here like this, and it's going to look something like this. So this one kind of looks like a little upside down heart, but that's the idea. And this is hitting at 3. This is hitting at -3. This, of course, is 0. And what we're going to see here is that theta is going all the way around 0 to 2 pi, because that's, what the angle is doing. So we begin here at the origin, and then theta carries us around all the way and brings us up to back around to here. So theta is going to be from 0 to 2 pi. And the radius is actually defined for us by this function. So our radius begins at 0 and goes out to whatever value the function is. So this is going to be r, and that's going to be the same everywhere. So no matter where we are, that r is going to be given by this function. So we can define our region, r, as being equal to the set of all r theta, such that r is equal to 3 plus 3 sine theta, not equal to, less than or equal to, back that train up a sec, 0 less than or equal to r less than or equal to, here we go, 3 plus 3 sine theta. Heavens. Okay, and then theta is going to be 0 to 2 pi. And there we have it. So these are the different ways we're going to describe our regions in the plane. So there's R, this is R, etc. This is R, I already wrote that one. So we're given some region, we're going to describe it in polar coordinates because in these instances it's easier to do so than it is to do it in rectangular coordinates. So now let's talk about how we change from rectangular to polar coordinates. So change variables from rectangular to polar. So going from rectangular to polar. All right, it goes like this. We have our integral over R of f of xy dA. That's going to be equal to the integral from a to b of the integral of g1 of x to g2 of x. This assumes g2 of x is above g1 of f of xy dy dx, right? Okay, well that is equal to, in polar coordinates, the integral from alpha to beta of the integral of g1 of theta to g2 of theta of f of r cosine theta, r sine theta, r dr d theta. Oh, and it just occurred to me, I shouldn't be calling these G's and F's. So let's call these H, because it's not necessarily the same function, right? I mean, it's representing the same thing, but I'm not just replacing X with theta. That doesn't make any sense. So I'm going to call these H1 and H2 of theta. Okay, so let's put a box around that, and then I want to really drive home this whole idea of the R dr d theta. So notice that dy dx or dx dy is equal to r dr d theta. Okay, it's like a pirate, r dr d theta. Yeah, I know. But the dumber it is, the easier it is to remember. Okay, r dr d theta. All right. But the reason for this is where is this coming from? We can talk about that for a second. So okay, so let's see where this is coming from. So we've got some region, right? Whatever this looks like. And just like in rectangular coordinates, we're going to break it up. Only this time we're going to break it up by radii and by angles, by our thetas, right? Okay, so if I take any one of these little boxes here, if you will, a little polar box, this angle change right here is delta theta, and then the width of this box here is r, right? Delta r, say delta r. But what is this little arc length right here? You may or may not recall that arc length, not the one where we have to do all kinds of crazy integrals, but just arc length of a curve, of a circle, arc length is going to be equal to r theta. Okay, so given this tiny bit of angle theta right here, we multiply that by the radius out to that point. So we multiply that by our radius out to that point, and that's going to give us our arc length. And so this little box is pretty close to r times d theta delta theta times delta r. So this is giving us the length, if you will, of this box, and then delta r is giving us our width of that box. Now, for any of this to work, our angles have to be in radians. So that's another note. I'll just put that right here. Note, angles, theta, must be in radians. If it's not, this stuff does not work out. Okay, so just to keep that in mind. But if you wanted to know where the r came from, that's it. So there's lots of good videos, there's good explanations, there's good stuff everywhere. You can check Paul's online notes, you can check OpenStax, you can check YouTube. I mean, there's a million different things that'll explain that to you. But just to give you a quick idea of where that r is coming from, that's where it's coming from. So let's get back over here to our main section. All right, so if we're going to switch from our integral over our region R of f of x, y, dA, that is going to become our integral from theta 1 to theta 2 of our integral from the function of theta 1 to the first function of theta to the second function of theta, our radii, and then we integrate that time, the function times r dr d theta. So don't forget that r dr d theta when we're doing our change variables. All right, so let's have an example. Go back to a brighter color. All right, so example, let R be the region bounded by the following. Be the region bounded by x squared plus y squared equal to 1 and x squared plus y squared equal to 5. Find the volume of the solid above this region formed by x squared plus y equal to f of xy. Okay, in other words, our z value. Okay, so there we have it. So we have a ring in the plane. X squared plus y squared tells us it's a circle with radius square root of 1, and this one will be square root of 5. So we have our region given by this circle. So this is square root of 1, and this is square root of 5. So that tells us our boundaries. So we have R between 1 and the square root of 5. Now our theta here is going to go all the way around. So theta should use a different color. Okay, let's see. Theta here is going to go all the way around 0 to 2 pi. So we have 0 less than or equal to theta less than or equal to 2 pi. So let's go ahead and set it up. So our integral is going to be going from 0 to 2 pi, that's our theta, and our radius goes from 1 to square root of 5. So in this case, it's very nice. They're constant. We don't have radius as a function of theta. All right, and then our function that we're integrating with respect to was x squared plus y, and we're integrating that with respect to the area, right? Well, we're converting this to polar coordinates. So we need to change x and y to polar coordinates, and then dA is going to be r dr d theta. So this is going to be our integral from 0 to 2 pi, integral from 1 to root 5 of. So now we set this up. We have x squared plus y. So x squared is going to be r squared cosine squared of theta. Y is r sine of theta. And then dA is r dr d theta. All right, so we can integrate this first with respect to r. I'm going to go ahead and distribute this r that was part of the dr d theta. I'm going to get that distributed so that I don't have to worry about it as a product. So this is going to be r cubed cosine squared of theta plus r squared sine of theta dr d theta. So we integrate first with respect to r. So this is what we're doing first. So this is our integral from 0 to 2 pi of. Okay, so I'm only doing this with respect to r. Any functions of theta are just constant with respect to r. So this is going to be 1/4 r to the 4th cosine squared of theta plus 1/3 r cubed sine of theta. And that's going to be evaluated from 1 to root 5 and then integrated with respect to theta. So these are our r values. We're going to replace each r. So this is our integral from 0 to 2 pi of. Okay, so replacing every r with root 5. This becomes 25 over 4 cosine squared of theta plus 5 root 5 over 3 times sine of theta minus, now plug in a 1, that's going to be 1/4 cosine squared of theta plus 1/3 sine of theta, and then we'll integrate that with respect to theta. Okay, so you'll notice now that there are no more r's in our function. Once we do our integration with respect to a variable, that variable should no longer be present in our expression. Okay, so now we integrate this with respect to theta. Actually, before I do that, I might consolidate a little bit. So let's see, I've got a cosine squared and a cosine squared. So 25 over 4 minus 1 over 4 is 24 over 4, which is 6. Cosine squared theta. 5 root 5 over 3 minus 1/3 is just 5 root 5 minus 1 over 3 sine of theta d theta. Okay, All right, so if we're going to integrate cosine squared of theta, we might want to use our identity that says cosine squared of theta is equal to cosine of 2. Cosine, let me write it down. The identity here for cosine of squared theta, that is 1 plus cosine of 2 theta over 2. There it is. So we've got cosine of 2 theta plus 1, all divided by 2. That's cosine squared. So we can make that substitution to make this a little bit easier to integrate. So we've got 6 times 1 plus cosine of 2 theta over 2 plus 5 square root of 5 minus 1 over 3 sine of theta, d theta. All right, we get some cancellation. That becomes a 3. So this is the integral from 0 to 2 pi of 3 plus 3 cosine of 2 theta plus 5 root 5 minus 1 over 3 sine of theta, d theta. And so that's fairly easy to integrate. It's pretty straightforward. So this becomes 3 theta plus 3 cosine of 2 theta. The antiderivative is 3 sine 2 theta divided by 2. So plus 3 sine of 2 theta divided by 2. Plus, and the antiderivative of sine theta is negative cosine theta. So this is going to be 5 root 5 minus 1 over 3 times negative cosine of theta. And then this is being evaluated from 0 to 2 pi. All right, so we do a little plugging and checking. We get 3 times 2 pi plus 3 sine of 4 pi over 2, which is 0, plus 5 root 5 minus 1 over 3. Let me try that again. That's absolutely illegible. One more time. Okay. Plus, all right, 5 root 5 minus 1 over 3 times negative cosine of 2 pi. Cosine of 2 pi is positive 1, so this goes to negative 1 minus 1. Okay, and then we plug in our 0 minus 0 plus sine of 0 is 0 plus 5 root 5 minus 1 over 3 times negative cosine of 0, which is again going off to 1. And so what we end up with is 6 pi. Because this negative 5 root 5 minus 1 over 3 and minus negative root 5 root 5 minus 1 over 3 is going to cancel. That's the point. There's that cancels out, leaving us with 6 pi. And again, because this is volume, if we were given units, this would be units cubed. Okay, so let's go ahead and do another example. So again, we're going to find the volume of the region enclosed by a petal. Actually, this one's not a volume question. This is an area question. So we're going to find the area of a region enclosed by one petal of a 3-petal rose. So if you're not familiar with this, a rose is formed by a function that's going to cause us to begin at 0, 0 and create something that's going to kind of repeatedly go through the origin. So a 3-petal rose kind of looks like this. I will draw a much better one for you. It's going to come out like this. Okay, it's going to look something like this. So if you'll just forgive my artisticness, here's what we have. So let me write all this down. So we're going to find the area in one petal of the rose given by r equal to 3 cosine of 3 theta. Okay, so we need to figure out where is this thing going, right? So first of all, because it's 3 cosine 3 theta, we know this is coming out to 3. So our radius is going to be minimum 0, maximum 3, and it's going to be given by whatever this function value is, right? So we're given the radius as a function of cosine. So we have that. Then we need to know what angle are we going to be running through. So at what angle am I going to be given this lovely petal here? Like, so for example, if I wanted to find the area of this petal here, what are the angles? Well, we can check this. If I put in theta is equal to 0, I plug that in and I get 3. So at theta equal to 0, I'm right here, right? So this is the point r theta. So that's going to be 3, 0, because my angle is 0 there. So this is my initial point right here. So this is where I'm starting for theta equal to 0. So then the question is, when do I get back to the origin? Well, we can find out simply by saying, well, when is r equal to 0? So when is 3 cosine of 3 theta equal to 0? When is cosine of 3 theta equal to 0? Well, it's equal to 0 if 3 theta is equal to pi over 2, right? Because cosine of pi over 2 is equal to 0. So that would work. So when pi over 2 is equal to 3 theta, or when theta is equal to pi over 6. So we know we're going to get back here if we have pi over 6 as our angle, right? Now that gives me half of this petal. So if I wanted to get the full petal, I could just double that. Okay, or I could think, well, when do I go backwards and get back here? Well, would get back there at negative pi over 6, right? So when my angle is at pi over 6, so right about here, I'm going to be back at radius of 0. Okay, so that's going to help us get this thing set up. So theta is going to go from 0 to pi over 6. The radius goes from 0 to the function value, 3 cosine of 3 theta. Okay, and the area is this times 2, because that's only going to give us half of our petal. And then we're integrating that over the area, which is r dr d theta. All right, so I'm not taking a volume here. I don't have another function that I'm working with, but the r dr d theta doesn't change. It's still taking the place of dx dy in our traditional xy rectangular coordinate system. So now we can go ahead and integrate this. So we have area equal to 2 times the integral from 0 to pi over 6 of, now we integrate r with respect to r, so that becomes 1/2 r squared, evaluated from 0 to 3 cosine of 3 theta, and then we'll integrate that with respect to theta. Okay, so to simplify, 2 times the integral from 0 to pi over 6 times 1/2 times, okay, so this will be 9 cosine squared of 3 theta minus 0. If you plug in a 0, you get 0. We'll integrate that with respect to theta. Pull the fraction out, 1/2 and 2 cancel. So integral from 0 to pi over 6 of 9 cosine squared 3 theta d theta. Again, we need to go ahead and use our trig identity. So use the trig identity again. So cosine squared of theta is equal to 1 plus cosine of 2 theta over 2. So if we use that to make our substitution, our trig identity, change this out with our trig identity, that becomes 9 times, so this will be 1 plus cosine of 2 times our angle, which is going to be 6 theta, because it was the angle here was 3 theta, divided by 2 d theta. So there we have it. So this is going to be our integral from 0 to pi over 6, 9/2 plus 9/2 cosine of 6 theta d theta. Integrating, we get that's 9/2 theta plus 9/2 times 1 over 6 sine of 6 theta. That's an S. All right, sine of 6 theta. And we're evaluating all this from 0 to pi over 6. So that's going to be 9/2 times pi over 6 plus, let's see here, I can take a 3 out and I get a 3 over 2, so that's 3/4 sine of 6 times pi over 6. So the 6's will cancel, we just get sine of pi. Okay, minus 9/2 times 0 plus, plugging in a 0, sine of 0 is 0. So this whole term is just 0. 0, looks like a 2. There we go. Okay, so what do we get? A little reduction here. We get 3/4 pi plus sine of pi is 0 minus 0. So it's just coming out to be 3/4 pi. And that's it. Again, since this was area, this would be units squared if we had any units given to us. And I think I'll end this one here. If you have questions about converting to polar coordinates, do please let me know. The big idea here is that we integrate typically with respect to theta last. So that's our external. And when we make our change for dA, it's r dr d theta. Not just dr d theta, it's r dr d theta. Okay, yes, as always, if you have questions, please let me know. That's the end of this one.